Good morning, one and all. Welcome to the second day of InGARSS. So, this is the first session. It's on ML application, machine learning application. We have 6 papers. I'm Dr. Ramya and with me Shilpa. So I'm from IISc and she's from
IIIT Bangalore, Faculty of Mechatronics.
So, we have 6 papers in this session. So each of you will be getting 12 minutes for your presentation and 3 minutes for question and answer. So we'll be showing this. The first presentation is by Sankalp and Hitendra Sarma. The topic is KMNET for Hyperspectral Unmixing. Have you made this?
Yes,
She is down.
yes.
So the biggest problem these days with the data is the data itself, because less than 1% of it is being analyzed and utilized. Good morning, everybody. My name is Sankalp, and I am here to talk about one such method wherein we utilize the data and analyze it. So, given an HSI, how do we extract in-member spectral signatures and abundances from them? I have designed an algorithm where we use sparse autoencoder to reduce its dimensions and also modified k-means to remove the noise, and it's a pre-processing algorithm basically, modified k-means. So the purpose of this paper is basically as I mentioned before, to extract n members and give out the abundances of that. This is done by restructuring a basic convolutional neural network. As said before, a sparse autoencoder is used for this. So these are the data sets on which I have experimented. Fine. So this is the overall architecture of this algorithm KMNet. So initially, a HSI image is given to the pre-processing algorithm, that is modified k-means, and then that is given to a sparse autoencoder wherein a latent space is being generated. That latent space is utilized to extract abundance maps and spectral signatures. So a traditional k-means, what does that do? We randomly select k different points and start extracting, start finding means and reallocating the centers with each iteration that we do. So this is the traditional k-means that we have. But the red points are, we call it as centers or pixels. Those center pixels may be real or may not be real, because when you consider 2 points, 2,0 and 6,0, when you take average of both of those, what do we get? 4,0. But here, this 4,0 is not something that is real. It's a virtual point that indicates center between two different points. Here, similarly, these red points may be real or may not be real. Correct? So what am I trying to do here is, consider these are the centers of the respective clusters. Now, I'm trying to find the nearest real point to this particular center. If that particular center is itself real, then the distance will be 0. So I'm trying to find Euclidean distance between the center and the nearest pixel to it. So this is the nearest pixel. The center has been changed to the real particular pixel of that. So this is what happens in the sparse autoencoder. After extracting all the center pixel values, all the n-member signatures, initial n-member signatures, this is given to the autoencoder. Here, utilizing a loss function, a latent space or a bottleneck is generated. This is the loss function. Let me go through each and every part of it. This particular one is initially root mean square error between this input and the output. Next, this is another loss function, that is KL divergence, which finds how input is different from output and gives us a loss function. And then the other one is regarding L1 regularization of the latent space or the bottleneck layer that we have. The other one is L2 regularization on the encoding hidden layer. into regularization on the decoder hidden layer. And the last one comes to into regularization on the parameters of batch normalization layer. Okay. Why do you think we are using L2 regularization in the encoders and decoders? Because here this is not a traditional autoencoder. This is a sparse autoencoder. Here only important parts are being trained. We can also say that only the active the only the important or only the from the whole image only the from the whole member signatures only the important features are being activated or being trained. So metrics that are used to compare the in member signatures that we got after the latest phase and the initial one. This is the spectral angular distance. This is basically cosine distance between the initial n members and the final n members. This is the root mean square error. The other one comes to spectral reconstruction error. This error basically what we do is we reconstruct what we have got with reconstruct the output and compare it with the input. So this is the spectral signature of Samsung ground truth, and this is the abundance of it. So using VCA, vertex component analyzer, which assumes pixels are linear combinations of pixels, and utilizing that VCA as a pre-processing algorithm, we get this particular graph as a spectral signature, and this particular map as abundance mapper, and with respect to k-means, those are the figures. So these are the metrics that I have got. For RMSC, I was able to improve the values for SID and SRE as well. So these are the individual values of each and particular n member that I have in the particular Samsung data set. So this is a ground truth of Jasper's data set, and the above is spectral signatures, and the below is abundance. And the same goes here as well. No. So these are the metrics that I've used for that. So I was able to improve the accuracy from 34% to 59% for Samsung dataset and 12% to 63% for Jasper's dataset. The future scope here includes changing the number of bands and checking with the n member signatures, and also estimating the number of n members with no prior knowledge with it. Like initially, I had while giving the input to k-means, I knew that I have 3 or 4 number of n members. But what if we do not have that number? How do we select k? That is the future work of this paper. That is also a future work of this paper. And also additionally, these methods can be extended to different applications such as environment monitoring, agriculture, and mineral exploration. Thank you.
How does your method compare to the literature not compared to the reference?
Yeah, I did, right?
So this is this is been the autoencoder. So this is your autoencoder, or this is your experiment, or this is some from previous results?
This is my experiment. However,
So actually, the previous paper has done
in the previous paper, VCA was used as a pre-processing algorithm.
so not still ever. So
Okay. Yeah.
How significant in the algorithm converging when you change the center?
Correct, correct.
What is the influence on changing the center? So your modifier means like you are moving your center point from virtual point to some point.
Real point. Yeah.
So how significant is this moving impacting on like how the changing is converging?
Got it. So basically, here we are trying to extract pure pixels, not virtual pixels. That will help us. That had help us in decreasing the error rate in my experiment, and also this is going to help us in help me in extracting the pixels which are not mixed, which are not mixed, which are really pure.
You also take quantitative assessment on this.
No.
Your
Yeah, correct.
so you need to say that by using this method, you need to be able to identify these.
No. Using this method, I can extract n members and n members spectral signatures and abundances of it. I did not exactly get your question. Come again.
What is the activity you are not part of it?
Please. So I'm basically extracting the n members. I'm reducing the dimensions. Like if you want to, if you directly take the n member spectral signatures from K means, it will be computationally expensive, which is why you can also observe that here. Here 0.021 is the scale is that. Here it completely got reduced. So I'm reducing the dimensions.
So challenge methods that are available for the hyperspectral unmixing. When you compare your performance with that. There are multiple methods which are available for this
Yeah,
unmixing.
yeah, correct. How how did
In terms of the reduction dimension.
the number of dimensions reduced were the same, but the error rate or the closeness to the ground truth that I have was less.
I just have a couple of related questions. This question was similar. What I understood from your modification and KMNET is like you are just relocating the centroid to a better place.
A real value, yeah,
Real value.
yeah.
Similar to that, how is it advantageous in any of the applications as well? Can you just cite some application wherein this would be helping in?
So this was basically an idea of mine where we were experimenting with different random values. So that was basically we did, I did not I went ahead with just selecting these particular values, not
How would it be
as said before, for this data set I had n members on the prior hand. So that was the number of k for us. So that was k fixed. Here, after selecting these values, these may be real or, as said before, these may be real or virtual. I went ahead with it, but the error rate was not satisfactory. Then I thought maybe reallocating it with the pure pixel, reallocating the center with the pure pixel that I have in this cluster. Yeah, Euclidean distance. This is one particular band, right? This is a 2D band.
Was there any reason why you selected Euclidean distance for that magic?
As this is the efficient, as this is the one, as this is for one single band, and Euclidean is a best one for a 2D distance finding. Absolutely. No.
And in the conclusion slide, you were mentioning the accuracy improved by this means from 34% to 59%, 12% to 63%.
One second.
I could not like just by this, was it helping district?
Give me a minute.
This is a tremendous improvement. I don't think this will
Resulting this kind of an improvement.
It could.
So the two data sets which you have experimented,
Mhm.
just by reallocating that center point,
Okay.
this happened with this one.
No, I'm comparing this result with VCA. VCA was
What is this VCA?
vertex component analyzer. That basically assumes that pixel is linear combination of vectors.
So why did you compare only with the, and this autoencoder using VCA? Do you have any reference related to that, which year it was published? That particular thing?
Come again?
VC, that particular algorithm was published in this year. Did you compare with any of the recent ones to make a comparison that it got improved in this way? Because I'm wondering about the change in the metric value. Just by checking the center point, will it help this way?
See, there was no algorithm previously, the whole architecture, I assume. So the whole architecture where this pre-processing algorithm was K-means or K-modified. This was not there before.
That is the thing which we.
Yeah, correct, correct. There were multiple different ones, Tmax T, VCA, and multiple other ones.
Good morning, everyone. So today the paper I'm going to present is Predicting Urban Expansion Using a Path Generation Land Use Simulation Model, a case study of Bangalore City. So this urbanization is an irreversible dynamic process. It's been happening in all of the mega cities all over the world. In India, it's majorly happening in Bangalore, Delhi, Bombay, etc. And when this rapid exponential growth of urbanization happens, it affects the ecology of that area. It affects the quality of life around that area. So we should have a growth which balances both, improve the quality of life, whereas it will keep maintain the ecology of the area as well. So we as an urban research scholars or urban planners should study more about what's the cause for this urbanization, what are the driving factors, and to what extent it will be growing in every year. And therefore, we can have a sustainable planning of every urban cities. So in the existing, we have different urban growth models. And here in this paper, we have implemented one of the type of a cellular automated models. So in existing cellular automata models and the CM model, which is implemented in this paper, the difference is that there are few disadvantages in the existing CM models. One is the rule mining framework. They are using a transition analysis strategy or a pattern analysis strategy. So in transition analysis strategy for each cell around a different time period, how the changes have happened, we are checking. But at that time, there will be different combinations for different land use types, and it will be computationally very complex to have that exponential number of combinations. That's one disadvantage. Another is the pattern analysis. In pattern analysis, we will avoid this exponential number of combinations, but we will understand or study the cell state only at a particular time period. We are not checking into how the temporal aspect of the change. And by all these disadvantages are being overcome in this new model plus model which is implemented here. So here the major focus of the study is we are understanding what are the driving factors caused for the study area which we have considered, and what is we are doing also a prediction of 2026 by using the land use land cover map of 2006 and 16. Also, we are validating how good this model, which is implemented plus model, is by predicting 2022 and comparing it with the ground truth, how well this model predicted. We are checking, and the major significance of this study is that we will know how we can do a sustainable planning for the urban development. And for prediction method, we are using linear prediction for the year 2026. The study area which we have considered is the southern part of the Bangalore. The total area covering is 4,216 kilometers square. The major data sets which we have used for this study, for driving factors, we have used from them, we have generated elevation map and slope map, population, distance to water, metro station, primary, secondary, and tertiary, which gives the connectivity, road connectivity, and distance to motorways also. One of the novelty or what we add from our part from the compared to the existing studies is that none of the studies in the Bangalore, when they're studying the urbanization, they're not considering how metro stations are affecting the urban growth. Only the primary, secondary, and tertiary or the motorways they are considering, but metro stations weren't considered much. So That's one of the thing which we added from our side for this. And we have general 120 training and 30 test polygons for each of the class. We have done urban water body and bare land, forest land. And land use land cover map of 2006 to 2016 we have considered. So now the role mining framework of this plus model, which is known as LEAS, land expansion analysis strategy. So in this first step, what we are doing is land use land cover map of 2 years we are considering. So here we have considered 2006 and 2016. We overlay one over the other, and we are checking how much the new cell state have been formed. We are not going back and checking from to two what have changed. We are not checking. That will give us exponential number of combinations. That's the major disadvantages of existing CA models. So we are overcoming here and checking all the new cells which have been formed, change cells have been formed, and we are creating a land expansion map. Along with that, all the driving factors which I mentioned in the previous slide. Along with that, we are correcting the sampling points for each of the individual land use type. So when we are when creating different subsets, we are creating 4 subsets. And when we are running the model, when we are first running it for urban growth, when we are running it for urban growth, we are considering urban growth and urban as well as the related driving factors. We are considering it as 1 and keeping the others as 0. We are running the random forest model. And from this, the output what we are getting is the driving factors. What's the contribution for each of the driving factor for urban growth, for growth of the bare land, for everything? What is the contribution of each of the driving factors? And we are getting the growth probability for the individual land use type, without considering the effect of the neighborhood effect or the future land use demands. So using this growth probability, we are now generating CA model is coming. So using that growth probability and future demand, how much the demand has improved. So here we are comparing the 6 and 16. So we already have the 2016 demand with us. So that is the impact of the future demand values which we are adding. Neighboring effect, we are considering a 3x3 window, and we are checking all through the LULC map, and we are considering in that 3x3 window, what is the contribution for each cell, how much is contributed for each of the land use type. So if more of the land use in that particular 3x3 window is urban, then we can say urban is having a more drastic changes happening in that small window which we are considering. Combining all these 3 things, we are getting the overall probability. From the overall probability, we are creating a rounded wheel. So in rounded wheel, we have overall probability of each of the land use types. 4 land use types which we have considered, all the land use type will be there. So for each iteration, which of the probability is having the highest value, that will be the iteration will be started. And then we'll go forward. And in the next step, what we're checking is, we check that for the particular cell state, does it had any influence of the neighborhood effect? If the neighborhood effect is 0, if there is no neighborhood effect, what we are doing is we have multiple random patch seeds we are generating. We are not generating it in a dispersed manner. We are following a threshold descent rule. So what we are doing is each iterations we are going behind and checking in the consecutive previous iteration, a particular land use type has been changed and how much the change has happened. If the change is significantly higher, then the threshold value will gradually decrease, and we are giving for that land use type to allow for this particular land use type changes, we are allowing it to happen in the coming forward iterations. And we are getting the final simulated LULC map. So here, the 6 LULC map is that, and 16, and the marked square point over there, that is the Kempegowda International Airport, which was built in this period of time, which is mentioned here. And here's the land expansion map, which we have generated in the first stage of the methodology. And this classification result, which we have accuracy, which we have got is 97%, and the cover status is 0.94. And from 6 to 16, the urban growth happened was from 12.5% to the 20.11% growth had happened. So using this 616 land expansion analysis lease map, we are trying to simulate the 2022 map to know how good this plus model is to develop a simulated LULC map. And we already have the ground truth LULC map we are generated using the QGIS. When we are comparing the urban growth area from the plus model is 20.31 and the actual LULC map is 22.55, giving an overall accuracy of 83.14 and cover classification as 0.75. And for the predicting the simulated LULC map, we are using linear regression method, which is already given in the plus software. And using the 2006 and 16, now we are predicting 2026. We have predicted a small, from only a small amount of time and half, 36, because we are using 6 and 16. If you want to predict 36, we have to take a different LULC map, and we can do for 2036 as well. Here we have considered short period of time, so 2026. So from 2026, we got 22% increase had happened from 2006 to 2026 for the built up area. And this is the simulated LULC map generated from the plus model. And this is the contribution, driving factor contribution by the built up area by the different driving factors. From this, what we are concluding is that connectivity is one of the important factor for an urbanization. It is motorways and railways. And the new feature which we added, the proximity to motorways, for proximity to metro, is giving a good amount of contribution, which was not considered in the few of the earlier studies. So proximity and population is one of the important factor driving the urbanization. So my conclusion is that here in this plus model, we have two rule mining framework, which is lease and cars. And here we are employed the plus model. And we have used an LULC map of 6 and 2026, and we have predicted for 2026. And we have checked the validation is done by you predicting by checking for year 2022. So one of the improvement which can be done for this existing study, which having the model was developed, existing model developed, is that here we are not considering the temporal aspect of the driving factors. We are considering driving factors only at a particular one time period, but LULC we are considering the temporal aspect. So if we can consider the temporal aspect of the driving factors as well, then we could get a better realistic ground scenario flow we can get. That's how I want to conclude. Thank you.
We have 4 minutes for. I have a question. You didn't mention the facilities, and also like our class. How are you getting the ground truth for the city of Bangalore?
City of Bangalore, we are taking a Landsat imagery, and with that using QGIS, we are classifying for the 4 different built-up area, vegetation and airlines, water body. We are classifying like that using the QGIS and Landsat imagery.
The ground truth, how are you using the ground truth? The label samples?
Label samples with the existing Landsat imagery, we are running the model.
Means it's like a region, certain regions that are already like sure that it is certain classes.
Certain classes, we are marked like that.
And this one, in fact, achievement. I can go to the previous slides. The impact growth yes. In fact, of future demand is like a change between the
like here 2006 and 16 we are taking. So 2016 what the amount of demand which we already have it in our area, the data we have. So we are inputting that and we are seeing how much the future demand has an influence.
Just it was a really good presentation. Yeah, you were telling like the present accuracy is 83%.
Yes.
And one of the future scope was considering the temporal aspect of the driving factors.
Right.
Once you try that, what might be the challenges you will face? Any insights of that? They implement the same.
They implement the same, but initially itself to get the temporal, the different timeline data for all these driving factors itself is difficult. To get the proximity to the motorways or the primary, secondary.
For the data for this?
For the connectivity, we have used the OpenStreetMap, and for the digitalization model and everything, we have used Google Earth Engine.
You should mention that as well, and even the references were also missing.
Yeah. 30 meters.
What will happen if you increase the distance? How will it affect your PMI?
So in some perimeter, if we are going for 60 meters or then the classification accuracy would improve. Initially itself in the training and the training data sets building itself, we can improve the better training data set we can improve. And when you run the model as well, thereby the final accuracy of the classification itself, we can improve if we get a final resolution of the ground truth or the final resolution of the Landsat imagery.
There is some already existing study which higher spatial resolution.
We haven't compared it.
How did you choose these different factors in the driving factors?
For the driving factors, which we have considered, reviewed the previous papers, which we have done for the area of Bangalore. And we have considered the major paper in which this methodology was developed as well. Comparing that, the major factors, they have divided the factors like socio-economic factors, connectivity factors, then some constraints. This water body on the constraint. Like that, they have divided in the paper in which this plus model was developed. Considering that, as well as in the previous literature, what are the driving factors they have considered. So in that, we have noted was the metro connectivity was not considered in papers. So we thought that we can include in this.
So do all these factors have equal weightage on your predicting, or do you think that some factors have more weightage? Did you consider a weightage for existing factors?
No, we haven't considered the weightage for.
So do you think all these factors are going to contribute equally to your prediction?
According to me, it's not going to equally, it's not going to, each will have different varying. Like the elevation and population will have a little bit higher contribution than the connectivity. So far.
Good morning, all. My name is Pratyush Talreja. I am a PhD candidate and a PMRF fellow, and I am working under the supervision of Professor Surya Durbha in CSRE IIT Bombay. So the title of my research work is Unmasking Devastation, Near Real-Time Earthquake-Induced Building Damage Detection. I'll quickly start with the golden circle by Simon Sinek, which states that you should always talk about why you are doing what you are doing, how you are doing what you are doing, and finally, what you are doing. So in my case, like, we believe that timely and accurate information about building damage assessment is important for recovery activities after the earthquake or any other disaster. And how we do it, like we have developed a novel and accurate information about the practical applications in the deep learning domain. And what we are actually doing it, we are finding the 3D change detection. So my data set is point cloud, that is 3D data, which belongs to X, Y, and Z direction, Z being the elevation. So as we all know that earthquake is one of the most devastating events, causing major damage in terms of loss of lives and infrastructure, which in turn shakes the economy to some extent. As we already know that in the start of this year, there was Turkey earthquake, which is considered to be fourth costliest earthquake on record. And the need for near real-time responses, we can save lives because we can get the information about building damages quickly as compared to the manual approaches that are being used currently. We can optimize resources, like which facilities we should give to which set of people which are stuck in disaster. Finally, we can minimize the economic impact and enhance the community resilience. In my proposed method, I have used pre-disaster and post-disaster point cloud data, and I'm performing 3D change detection. So talking about the current humanitarian efforts, so traditional methods like manual surveys, field inspections, and data collections are being done, and which have limitations in terms of speed, accuracy, and scalability. I'll take the same example of Turkey earthquake, wherein people were taken out even after 15 days. So they were buried inside the rubble and the debris. So that process is very slow, and that is not as accurate as compared to the current methods that I am developing. Now considering LiDAR data, that is the point cloud data, so we get information about the geometry of a structure. So LiDAR plus drone plus deep learning is what we are trying to do this time. One more thing is if we can integrate the method that I've created, like deep learning method, along with some traditional method for verification purpose, that can give some better results. Now, there were two motivations for me to start working on this research work. First was the challenges, and that is the search and rescue difficulties that I've already mentioned. There are inadequate, I'm so sorry. Inadequate infrastructure. So several damage to critical infrastructure such as roads and bridges. Finally, limited access to affected areas. Because of the earthquake, people get stuck and facilities cannot reach people that time. And finally, communication breakdown. We cannot communicate with the affected areas, people in the affected areas. Finally, what is the need? So time sensitive search and rescue operations can directly correlate with the chances of saving more lives as compared to the manual inspection. Second is will optimize resource, minimize economic impact, and enable informed decision making. So government can basically make informed decision about allocation of funds and implementation of recovery plans. First, I'll talk about the study area, then I'll go to the proposed solution. So for my study area, I have used Kumamoto earthquake dataset, that is 2016 Japan earthquake. And I have pre and post LiDAR data. So the pre-Kumamoto earthquake, that was on 14th April 2016. And the post-Kumamoto earthquake, that was on 16th April. So just before I go to the proposed solution, I'll just explain why it is called pre-Kumamoto earthquake. The thing is, there was one earthquake that hit on 14th of April, and the data was taken on 15th of April. Again, a major earthquake hit on 16th of April. So the 14th one is considered as foreshock, and 16th one is the main shock. So that is why I call this pre-Kumamoto earthquake. This will also have damaged buildings, but not to that extent. Like in 16th, that is post-disaster, post-Kumamoto earthquake data, there will be destroyed buildings, but for pre, it will be only lightly damaged buildings, for example. So this is how my data set looks like, a snapshot of the data set, which shows trees, roads, and some buildings in the picture. Now, basically, our solution is first is we should always pre-process the raw point cloud dataset. So the point cloud dataset is unordered as opposed to the images optical dataset. So first we'll do pre-processing of the dataset, that is, we'll remove the outliers. Second is we'll extract the buildings. So in our urban area, there will be buildings, vegetation, roads, and other objects also. So we'll just extract the buildings because we have to perform building damage estimation. Finally, we'll extract the features. We'll see what those features are, and then we perform the classification. So we have used point net architecture for that to perform the classification. And finally, we give the damage map. Talking about the pre-processing, we have this library PDAL, that is point data extraction library, which is employed to apply K-means algorithm, because first we have to remove the outliers. So the same objects, the clusters will be form of same objects, and the outliers will be separated out. Second is performing pre-processing, like gives the point cloud in an efficient manner because the size is less and we can perform computation faster. Talking about building extraction, that was the second part. These are the PDAL pipelines that I have created. So pipeline 1 is used to extract the buildings from the data sets. For example, in an urban area, there are 100 buildings. So in pipeline 1, you will get all those 100 buildings. Pipeline 2 will basically clip out each building separately because we have to give that as an input to our deep learning architecture. So talking about pipeline 1, as you can see here, in limits, classification 6:6 is written. So in LiDAR, every object is given some class code. Like building belongs to class 6. So that is why I have written 6:6. So out of all the objects, I'll just clip out all the buildings. Second is, if you can see on the second paragraph, polygon building.shape. So we are giving shape files of that particular polygon so that we can clip out particular buildings from that LiDAR dataset. In this way, we have extracted all the buildings. Now comes the feature extraction. So here what we do, like we have calculated eigenvalues because LiDAR dataset is basically multidimensional, three-dimensional basically, XYZ, but along with XYZ, we have got intensity, return, angle, and all other things, other factors. So first what we are doing, we are trying to calculate eigen-based features, that is surface roughness. Surface roughness means basically if the roughness is more, that means that building can be considered as damaged. Based on what the surface roughness is, we have divided into three parts, like it is undamaged, moderately damaged, or completely destroyed. Then comes the planarity. The more plane it is, the less chances of it being damaged. Linearity talks about the edges of the building. First talks about the roof of the building and facade of the building, but this linearity talks about the edges of the building. Then finally, we have elevation based difference. So previously in pre-earthquake, if a building is of suppose 10 meters and after earthquake, if it is 5 meters, for example. So in that way also, we can divide our buildings into different degree of damages. Finally, the classification. So here we have used this point net architecture, basically input point clouds, that is n cross 3 that we are using. And we are using input transform. Why? Because point clouds are unordered. So, and we have to make it rotationally invariant because there can be different combinations. So we use this TNet to make it rotationally invariant, and then we provide that MLB, multilayer perceptron, to calculate other features. Again, we make the feature, we do the feature transformation, we make it invariant because first we are expecting the local features. Finally, we are expecting the global features after applying the max pooling. And after it goes through that MLB, we get the output scores. So those output scores belong to different classes of how many number of classes we have. The second part is segmentation, which is not implemented in this paper. We have just implemented the classification part. Now, after performing these operations, like how do we see that if the building is damaged or not, for example? So first is when we plot graphs of a particular point clouds. So these are the point clouds. So left one is the undamaged building. You can see the roof that is clear in the picture. Second is the damaged building because that building has fallen off and there are some debris. Again, some visual interpretation. As you can see, there are 3 buildings. This is the pre-earthquake LiDAR. As I've already mentioned, there will be some lightly damaged buildings also. So this building is lightly damaged, but other 2 are not. If you check that in the post-earthquake LiDAR, all are destroyed. That was on 16th April. I have just mentioned this part, but if you look at this image also, this particular building also, this is not damaged here, but that is moderately damaged on the post-earthquake part. Finally, like we give this kind of damage map wherein there will be undamaged buildings. Red are the completely destroyed buildings or heavily damaged buildings, and the purple ones are the moderately damaged buildings. So as of now, the accuracy was around 81.2%, not as good, but for that, the future directions what we have thought of is increasing the number of buildings, data set basically, because deep learning architectures are data hungry. Second is we want to evaluate more features. Like as of now, we have evaluated planarity, linearity, and surface roughness. We want to evaluate more features. Second part is what we are trying to do is we are fusing LiDAR data with the images. So we have got the Earth satellite image from the world view. So what we are trying to do now in the future work that we have already started, we will first determine if a building is damaged or not in terms of optical data. Second, for those damaged buildings, we'll find the degree of damages using the LiDAR data. Third is to make it universal, we have to experiment with different kinds of disasters also. Like flood is one of the things that we want to work on because using the LiDAR dataset, the nominal wavelength of the LiDAR is 1064 nanometers, and that will be reflected from the top of that water level. But for that, some different kind of LiDAR is used, that is 532 nanometer wavelength that goes inside the water and checks about the length of that particular water that building that is submerged inside the water. So we want to implement that also after this. Talking about the summary, as I've already mentioned, that LiDAR provides rich information about the geometry, about the scan environment, which can be used during the disaster. Second is we have developed this deep learning method, which detects the damaged buildings without any manual intervention. Finally, as of now, the accuracy is 81.2%, but it can be applicable to other disasters also. And these are few references that I have used in my slide. Thank you.
Yeah, exactly 3 minutes for the question that you think. I have one. What is the source of this LiDAR data?
So this is openly available on Open Topography. Open Topography, yes. This is freely available, but that is unlabeled. You have to label it.
Do you have any baseline, like you are 81%, but is there any baseline of previous pictures that we can see, okay, your method is improving 10% of what you have?
Yeah, so basically there are different architectures. So as of now, this is PointNet is one, there is PointNet++. There are point pillars, which uses the voxel based. So like we have pixels in images, we have voxels in 3D data. So they are using voxels to do this classification part. So we are comparing it, we are improving our PointNet architecture also. because as of now, there are no transformer-based applications to point cloud classification. There are some point transformer, for example, but they are not applied to the disaster area. So we are trying to implement that as of now.
So great presentation. I think I am more curious on why LiDAR and not visual representation. The end goal is to see the perspective.
The thing is, we are talking about the degree of damages, which becomes a bit difficult in terms of visual interpretation. So LiDAR talks about the geometry of the structure, not only the height differences, but other kind of geometries. Like we have calculated the eigenvalues, we have calculated the surface roughness and other features. Those can be calculated easily using the 3D data structures. Like if we take an example, if you show some child, for example, an image and ask him or her, like if it is moderately damaged building or highly damaged, if you show the 3D structure, that is more visually appealing also, and then we calculate it easily. So that is why we are into 3Ds as of now. But combining it with image will definitely give better results.
One question, what approach you use for building extraction?
Building extraction.
What approach you use?
So I mentioned this PDAL library.
Did you check with other approaches or can we rely on this?
So basically, we have taken this building footprints from OSM. Just we have extracted those buildings from the top of this. So second approach is like that is in my future work of doing that building extraction, building footprint extraction. That is we are yet to work on.
About, you were mentioning about assessing the degree of damage.
Yes.
So what can be the possible quantitative measures which will give you that idea?
So as of now, as I've already mentioned that, so we have done this in 3 parts. First was, this was unlabeled dataset. So we labeled it manually. That was a task for like 3 months. So we did it manually using this visual interpretation that I've already mentioned. Using that, we have like divided into moderately damaged and heavily damaged.
Quantitative measures we use?
So for that, we have used these features. So there are different features. We have evaluated this feature. So the best feature is surface roughness. So first part was,
You are yet to do.
no, we have done that. So first part was we did it manually. Second is we calculated it using the surface roughness. We have pre and post LiDAR. We checked the surface roughness. We have calculated it. So for surface roughness greater than 0.8, we consider it as heavily damaged. We have divided that into different thresholds. No, that we are still working on, and that is part of the journal work. So
And if the references, that is not the right way to mention the reference.
sure, sir. Thank you.
You can configure it.
Thank you, ma'am.
Some questions?
Sorry.
You use the shapefile to extract the building. So, I mean, you use PointNet as well. So why didn't you use PointNet to directly classify that data?
So basically, ma'am, like when we provide some data set, so if we don't have the building extracted, like if we see the PointNet papers, they have used ModelNet data set, wherein they have different objects. Like for example, airplane, they have separated out the airplane, for example.
PointNet paper was developed for a Kinet data.
Yeah.
But actually, there have been lots of work in this PointNet has been used for airless data like this.
Yes.
So the question is, you can directly use PointNet for your building classification.
Yes, ma'am.
So why was not right? And
No,
the
ma'am,
main question is, you use some shapefile for extracting the building. If
Yes.
suppose the shapefile has some of the buildings missed,
Yes.
source and data set.
Yes, sir.
So those buildings will not be detected.
Yes, definitely. And so that is my next objective that I mentioned, that we are working on building footprint extraction. So that we are currently working on.
So you try to PointNet itself. PointNet
Yes.
is the classification.
Yes, ma'am. Yes.
The accuracy of the building detection is actually the accuracy of the building which is present in the OS, right? It's the 18%.
Yes. Out of those, yes. Definitely, ma'am.
So good morning, respected faculties, experts and scientists who are here, and my fellow scholars. So first of all, I'm grateful that we've been given this opportunity to present this paper, our paper that we've worked on. So as the title suggests, this is active learning using multi-feature sparse kernel sparse representation classifier for the hyperspectral image classification. So basically, we all know what image classification is and what is a hyperspectral image. So basically, we have an image. We all know what is an RGB image. And when we deal with, it has only 3 bands, and multispectral, we have maybe 10 to 12 bands. So a hyperspectral, basically, it has hundreds of bands spanning across different wavelengths. And so because of that, it has a lot of rich spectral information. So this rich information, it can be utilized for various purposes, such as environmental monitoring, crops analysis, land cover analysis, so all of these things. And one of the ways to do this, and a more efficient way to do this, is of course using the supervised hyperspectral image supervised method of classification. So basically, what that is assigning a class label to each pixel in the image based on the label samples that are available. So of course, there's challenges when it comes to supervised, as always, and even in yesterday's talk as well. This is a challenges that is there even today, as of that is still there. So label samples is always expensive. We need photo interpretation, we need field survey, so that's quite expensive. And so that's why, like currently, what we're facing now is we have very limited label samples, and a lot of unlabeled samples are there. So there are different ways to deal with this. So the first way is semi-supervised learning. So basically, it involves the selection and addition process of the unlabeled samples to the training set in order to improve the classifier. And the active learning is basically what it does is it selects and adds only the informative samples. So we select only the informative samples. We add those to the training set, and in order to improve the classifier. So this has a tendency to leads to less redundancy. And of course, when we select only the important samples, we need only very less rather than what we have from semi-supervised, and that's why the computation cost is reduced. So this is the framework of the active learning. So basically, it selects informative samples from the unlabeled pool. After that, it goes through the query function. So the query function will select the most informative samples. And after that, only a few informative samples will be given to the supervisor. So that will be labeled. That will be added to the labeling pool. And after that, this will be classified. And after that, this process will continue until we have enough label samples or the performance have improved enough. So that's when we stop. And the fundamental of active learning is always the query function. So basically, there are 2 criteria that are there: uncertainty criteria and the diversity criteria. So the uncertainty criteria, from the name itself, so this is used to select uncertain samples. Uncertain samples are those samples that lies at the boundary of the classes. For example, we have, let's say, class 1 and class 2. So there are certain samples that lies at the boundary of these classes. So those are usually uncertain. That is very difficult to classify and may often lead to misclassification. So what active learning does is tries to select some samples from those regions in order to improve the classifier ability to classify these different pixels that are there in the image. So the diversity criteria, of course, when we select these uncertain samples, what happens is that sometimes we can select only from a cluster. So we don't want to select only from a cluster of samples. So we want to select from different parts of the of the boundary region. So that's why we need a diversity criterion as well, so to select diverse samples. So these are some examples of uncertainty criteria that is there. And of course, some certain examples of diversity criterion as well. So the motivation, so we've seen that most of these in the literature that we've seen is that the uncertainty and the diversity criteria that is there in the literature, they use only the spectral information. And of course, we've seen also that the multi-feature approach, so they have shown very much encouraging results for the hyperspectral image classification. For example, this is just a figure to show that one. For example, we have 3 features. One could be the spectral feature, one could be the spatial feature, one could be the texture feature. So these features will have different perspective of the image, will give us different perspective and different discriminatory power. And so that's why when we combine all of these, we get better discriminatory power and better representative power. So that's why leading up to that, so that's why we have embedded this multi-feature concept into our query function. Now, earlier we have also proposed uncertainty criteria as well as a diversity criteria in our previous work. So to that, we've now embedded this multi-feature concept into it. And so that's why we call this the multi-feature KBT, kernel breaking tie, and as well as the multi-feature dictionary correlation-based diversity. Just a little bit, we'll go slightly into the background of this method before we go into our method that we have been proposed. So what is sparse representation classifier? Basically, from this image, we can understand we have an unlabeled pixel. We have what we call a dictionary. So dictionary contains atoms or training samples from different classes and the sparse coefficient. So what sparse representation does is, basically it tries to find a linear combination of these unlabeled samples using the dictionary. And so the class that gives us the best representation, so that will be assigned to the unlabeled samples. So that will be assigned to the unlabeled samples. And of course, we have the function that is there, basically just tells us that the class that gives us the minimum residue, that means the minimum error, so that will be assigned to the unlabeled samples. And so we're dealing here kernel because like we don't want to deal in the feature space. Now in the feature space, normally what happens is that similar class are very difficult to differentiate and so that's why we are dealing this in the kernel space to have better separability between the classes. And so just briefly, although this is a function, but let me just tell you basically that let's keep our focus here. So what we're trying to do here is we're trying to find, again, like I mentioned, the class that gives us the minimum residue and the second class that gives us the second minimum residue. So we find the difference between them. If this difference is very small, so this tells us that this lies in the boundary, that this sample lies in the boundary. If this uncertainty value is very small, it lies in the boundary, and that means this sample is uncertain. And briefly, this one also I've put here, but let me just focus on the red comments there. So basically what it does is we compute the correlation between these uncertainty samples and the dictionary, and the samples that give us the minimum correlation to the dictionary that will be added to the dictionary, and I'll explain this further in the later part. So here, how are we going to fuse this multi-feature? Basically, the classification confidence that we get from each feature, well, feature 1, feature 2, feature 3. So we combine all of those together in order to get the total classification confidence. And as I mentioned, this value will tell us that if it is very small, that means this is an uncertainty sample. And if it is large, that means this sample belongs to a particular class, so we don't need that one. And so among the uncertainty samples that we've collected, so we will choose only some of them to give to the supervisor. And so this as well, we combine all of these from the different features. The difference is only there that I've highlighted. So we fuse together the correlation from different features. So this is basically just a rough idea of what our proposed technique is. So we have this dictionary space, and we have this a lot of unlabeled samples. So what we're trying to do is we start first from a very small part of our dictionary space, and we try to expand a little bit at a time using the dictionary correlation-based diversity. So we try to expand a little bit at a time until we have enough samples. And so, yeah, to evaluate this, we've used two data sets, Indian Pine and University of Houston. And yeah, so we've compared two experiments. That is, first we try to evaluate our uncertainty criteria, and the second is we try to evaluate combining uncertainty and diversity criteria as well. And for this particular paper, we have choose three features, that is the spectral feature, the EMAP, and the DMP, differential morphological profile. And so these are the results that we've obtained. So at different label samples that is there, so we can see the accuracy and the standard deviation that is given here. And so as you can see that our proposed technique, it gives a significant increase from our previous method as well, from 74 to 82. And similarly for the Houston data set as well, it has given us a 1% increase from the previous method. So this is for the second experiment that we have. So the second experiment also shows that, as you can see here, the curve line that is here. So at each and every number of label samples, so the proposed method, it always gives a always a better accuracy or similar accuracy to the previous methods. So just like summarize. So for the Indian Pine dataset, what we've seen is that it gives us a significant increase of 82% from 74, and even for the Houston from 85 to and which is much higher than the others. And for the second experiment, when we combine all of them, it shows that it increased the accuracy even further. So from 82 to 83 and from 85 to 86. So just in conclusion, so the multi-feature sets, they have improved the HSI classification, and because when used correctly, they can complement each other, these different features. And so most of the AL techniques that we see, they do not exploit the strategy and use only the spectral information. Therefore, in this paper, we have proposed the uncertainty and diversity criteria as well. And we compared the results. And as you can see from the results that our proposed method, it gives better accuracy. So yeah, that's my methods. So thank you so much. If there's any questions.
Any questions from the audience?
Any questions or maybe feedbacks, if you can give me, it'll be helpful.
I have a question.
Yeah.
This great presentation, thanks for comparing numbers also. So typically, uncertainty or clarification, they depend on what training was used to find that answer. Every time you have a new training.
We have first selected some samples. We have to select some samples. And after that, we keep on adding to that training set. And so that will eventually improve the model and then help us find more uncertainty samples. Like that. As I've seen shown in that diagram. So once we've selected one, we try to add to the labeled samples. And after that, we classify again and try to find more uncertainty samples if we need to. Or for example, if our classifier have improved enough, then we stop there. And if not, then we continue with that process.
My question was
Calibrating in what sense?
basically confidence of one checkpoint will be very.
Yes. So
Non-pricing uncertainties across run.
okay. Yeah, so that one, it has been validated based on this based on the accuracy that you get. So every time you evaluate accuracy, so every time you check if your model is improving, and definitely it will keep on improving. Once you see that there's a dip, that means you don't need any further uncertainty samples that are, or maybe like it'll just create a noise. So that's when you stop the model from running any further. Yeah.
Just a simple question.
Yes.
It was really good presentation. And how about the use of any meta-heuristic optimization about it for improving?
Optimization. Okay.
Because in your work also, what I understood is like randomly you're selecting samples and improving over the iterate.
Oh, no. We are not randomly selecting samples. Like I mentioned, we need a query function. So
Suppose you're selecting samples based on that. What about the use of any optimization algorithm for the same? Will it help or not?
Optimization here. Okay. Optimization could probably be added here to help us find quickly the uncertainty samples. As we know, in the spectral space, there's a lot of areas to cover. So maybe with our optimization approaches, it can help us find uncertainty samples more quickly, much faster than what will be only if we use this approach. Yeah. Yes. Thank you so much. Yes. Oh, yes. Actually, this is the dictionary space.
No.
Or the features. Okay. Oh, features. Okay. Yeah. This one.
So, have you tried on what is the effect of these features on the classification? Like if you use only the.
Oh, yes. Yes. I did that. So that's why, like, when we do this one, only the spectral here I'm showing. So all of these use only spectral method. So only the spectral information. And of course, from the previous experiments also, when we can see that if we use only DMP and only EMAP, so it's always lesser than when we combine together.
The classes, if you have different classes.
Yes.
You have plotted the overall activity.
Yes. Yeah, the classes I have not missed.
class accuracy.
Okay,
Each
okay.
method, like, maybe for some
Yes.
class might be performing well.
Yes, yes, yes. Yes.
So we can try such a-
Yes, that one we've tried, but unfortunately I forgot to present here.
But
But
if you can just comment like how it was like affecting.
okay, okay. So basically, what I've seen from their results is that usually it can be a problem if we have these classes that are very small. So for example, the number of samples is very small. For example, the object in the image is quite small. So that sample will always be treated as with, it can have some certain noise. So what this technique, the disadvantage could be is that it could choose only the samples of that class. So that could be a problem. And if we consider this one, from what I've seen from this experiment is that so far from these two data sets, maybe for other data sets, that can happen. But for these two data sets, that did not happen at all. So it tries to select samples from each classes.
That is the problem of the class balance.
Yeah, yeah.
What I'm asking is like a spectrally similar class.
Okay.
If you have like in the.
Yes,
data
yes,
file,
yes.
you have, like,
Yes, yes,
very
yes.
spectrally similar
Yes, yes,
class.
definitely.
Other classes, they're like very. Different.
Yes, yes, yes.
So what is the effect of this algorithm on a spectrally
Oh,
similar?
yes, 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 definitely, ma'am. So what we've seen is that, yes, it has improved a lot. It is improving the accuracy, and that's why for the Indian pines, the results, if you see, even for the previous methods also using only spectral information, it is this particular data set, it has a lot of similar classes, and so we do not get that much of accuracy. So here from the results, we can see from 74 to 82, it is showing that there's an increment in the accuracy also, even among those classes. Otherwise, if it doesn't improve, that means that this accuracy won't be high, and like it'll be like the previous methods that is there. So definitely it has improved even among
Last
those.
question,
Yes.
just on the computation process, like that.
Yes, yes.
How-
So here, the computation I've shown. Am I showing it now? Okay, so here it depends upon the parameters that you're choosing. Here we're choosing only 3 samples per class, and after that we're adding only 5, and we're running 30 iterations. So as I've mentioned, like this could change based on the parameters that you're choosing. For example, you could choose 5, you could choose 10, and depending upon the accuracy that you have that you desire, or the model that you desire, model performance that you desire. So you can stop there. But for here, because it's running multiple iterations, so definitely it is taking some time. Yeah.
So, good morning. I am Thogarcheti, and I will be presenting our paper, a time series prediction of multispectral satellite images and its application for cloud removal. This paper is co-authored by Ankita Saha, Ritaban Ghosh, Professor Jayanta Mukhopadhyay, Professor Sudeshna Sarkar, along with me. So, objective of this work is that we want to build a model that can extract spatiotemporal features from data. The same model should be able to predict if some bands are missing from some specific date, and we want to use this model for cloud removal as well. So we want to give a set of images where the band values are present along with the time and date, and we want to predict image where the band values are not present, but the time and date are given of the same area. All this sequence of images needs to be of the same area. Now, if we formally define the problem, so XBTI, we are representing that X is the image, B is a specific band index, and TI is the timestamp index. So we represent the image as X1 TI, X2 TI, like this up to X7 TI, then year encoding and month encoding. Here we have used 7 bands of Landsat 8 image, that is from band 1 to band 7. Those are postal aerosol, red, green, blue, near wave infrared, short wave infrared 1, short wave infrared 2. Now, we design a masked image as XMTI where the band values are masked to 0 and the date information is provided. And the problem is that given at least one masked image and a sequence of images of the same area at different timestamps, we want to generate the same images along with unmasking the masked image. And in this experiment, we have used a sequence length of 6. And here the timestamps need not be equispaced. So the time gap between T0 and T1 may be 15 days, and T1 and T2 may be 30 days. And our model should not be affected by that. And that's why we are providing the month and year encoded along with that. So in the method, first we need to do certain pre-processing to train the model. So first, we found that when we are taking Landsat 8 images, the pixels are not exactly co-registered. Each pixel is 30 meter cross 30 meter. So it is sometimes that about 5 meter or 10 meter, it is different for different timestamps. So we need to align them or co-register them to represent the same point on the map. Next, we create small patches, about 64 cross 64 patches from those images. And then we encode the date and month. And after that, we prepare the data set. So in encoding the date and month, one of the problem is that if we take directly the distance, say December and January, if I am representing December as 12 and January as 1 of 2 different years, suppose 2001 and December and 2002 January, they are close. But if we are using the number values, due to that, we will get a very large distance. For that, we are encoding the month using this function, so that which has been plotted there as well, so that the distance between December of 2001 and January of 2002 would be less. And for encoding the year, we are taking the present year of the timestamp year minus 1970. This is so that we deal with a bit smaller numbers. So while creating the data set for training, as explained, we are having 7 bands and 2 bands for the timestamp. One is year and one is month. So in the input, we give a sequence of images. Here, in this case, a sequence of 6 images, but some of the images are masked. Where in the masked image, only the band values are masked, the time is not masked. And in the output level for the training data, we have the unmasked images along with the timestamp data. So here, while training the model, we only use non-cloudy images. Now in the model architecture, we are using a vision transformer where we have encoder layer, the transformer layer, and the decoder layer. So here we are in the input, some of the images may be masked, but all of them cannot be masked. And at least one image is masked while training. And in the output, none of the images are masked. So, yeah. So for the cloud removal application, we are masking the cloudy image and giving a sequence of non-cloudy image of the same region, which are co-registered. And we prefer to give the images of nearby timestamps. Though the model works with other timestamps as well, but it gives better result if we are using nearby timestamps in the cloud removal case. So first we mask the cloudy images, then we pass that sequence and get the output. So this will give a unmasked image of the cloudy image. Now we identify the cloudy pixels in the input image, the given cloudy image, and for that we have used a simple threshold on the green channel. And after that, we retain all the pixels that are non-cloudy in the original image and replace the cloudy images with the model output. So we have tested this on Landsat 8 data on Kharagpur region, where the WRS path is 138 and WRS row is 45. So the training parameters that we had used is we used Adam optimizer with learning rate as shown. With weight decay, we used leaky deluge. We had tried with other activation functions and we found that leaky deluge is giving the best result. And we used mean squared loss along with root mean square loss. So this is the results. So we find that the model is having similar train and validation accuracy, and we found that the root mean square error is 547. And when we compare the cloudy image with the non-cloudy image that we found with respect to the non-cloudy pixels, we found that the peak signal to noise ratio is between 30 and 33 dB. So here, this is the cloudy image for which we want to remove the cloud. So after thresholding on green channel, we get this cloud mask, where white pixels are the cloud and black are the non-cloud. And that predicted image is the output from the model. Now, using this mask on this, we keep the pixels that are non-cloudy, and for the cloudy pixels, we take the values from that predicted image. And after that, here we are having 7 bands in this. Here we have represented only RGB value. And here we have calculated the NDVI and NDWI for this one is for this, and that one is for this one. Now, what we find is when in these positions, the clouds are there. And after removing the cloud, we can distinctly observe that those portions are coming correctly. But here, one of the things is that here some clouds are there which are not detected. So we need to improve the cloud detection method. So in conclusion, we have proposed a method which can remove cloud, and it can be used for image compression as well. So after whatever output we are getting here, that is the representation of the image. So in that way, we can have a compressed representation, because in the end, the decoder would generate the same image as well. Yes, there would be some compression loss. That is the error in the model. But to some extent, it is giving quite good results. And we can also use this for predicting some specific timestamp. For example, Landsat 8 data we have every around 15 days. So suppose we want, we have data on March 15 and on March 30. We want on March 20. So for that also we can use this by encoding. Now, in the future work, we are working on Sentinel-2 images. So because Sentinel-2 has better resolution for 4 bands, that is red, green, blue, and near infrared. We are using those and checking what we can do. And for cloud detection, we have used a simple threshold, and we see that there are some parts that are missing. So we are trying to improve that method as well, so that we can detect the actual cloud, so that we can replace them. So thank you. Questions? Yeah.
You have used this time and year and month as a for encoding.
Yeah.
So I'm sort of using hours also, because that will have impact of sunlight. So based on that, your battery or reflecting certainly of that.
Yeah. So basically, the thing is that in Landsat 8 data, we are not having the same date, different times images, right? We have image of one date, and then after 15 days we have the image. So that's why we have not used, but those can be incorporated. But one of the disadvantages would be the computation would be increasing for that. Even for if we want to incorporate the date, we have used month and year only here. We can incorporate the date as well, but that will also increase the computation, but that would be needed, and in the future, we are working on that as of now.
The question is, when you are masking things, so to certain timestamp, so you are masking randomly in the 6 timestamp, or you are fixing first timestamp and then
Randomly, and while training the data, it is not necessary that we have masked one band. We have masked in at least one, at most 5, because we have the sequence length of 6 in this case.
Concisely mention what is the novelty of the work which you have executed?
Yeah, so no, firstly, that we are trying to predict. We want to build a single model that can do feature extraction of based on time as well as space. Secondly, that model needs to be able to do cloud removal, and thirdly, it should be able to predict image of a given timestamp using other timestamp images of the same region. So we want to have a single model that does all this work.
The results what you have shown, I think you were focusing more on the application side, the cloud removal.
Yeah. So we are more focused on that, but this feature extraction is all like cloud removal will work after we have got the prediction of a certain time, and in the architecture itself, it is compressing the image. So if we suppose
What's that slide number 8?
slide 8, yeah.
Here you are fixing the threshold wave channel validity.
Yeah.
And what is it? Is the relevance?
So we empirically tried and found that this is giving quite a good detection of cloud, but there is scope for improvement on this.
Means that it is particularly for the data set which you have used.
Yes. Yes.
For automating this entire process, you'll have to change.
Yeah. So we are trying with different clustering methods, so that if some clustering method can detect clouds and non-cloudy pixels.
So generally for any approach, prefixing a value like this,
Yeah.
which is quite image dependent, is not a good way.
Yeah. So we found that for Landsat 8, it is working. We have not tested it on other images. Like we are currently working with Sentinel-2, and firstly, we are training the model, because in training the model, we do not need this cloud. Then in the second part, we are planning to use some different clustering methods so that we can automatically detect the cloud images without this threshold bottleneck.
What was the size of your data set?
We have used this this area we have used, and there were about 40 images. And so with the 30 images we were training, and the rest we are testing. And these images, by image, I mean that whole Landsat 8 image without considering the no data value. And then we are cropping the image in 64 cross 64 patches. So the number of passes through the model is increasing like that.
And you plotted some loss curves. What about the accuracy plots?
Since this is a regression task, so we are not using accuracy, because we do not have any class levels. We are trying to predict the band value. So we are trying to find the difference between the band value using RMS.
The comparisons what you have made to the cloud, that application what you have mentioned, it's only qualitative subjective comparison or quantitative data.
So for quantitative, we have this PSNR value, but we need to work further on that. Like how we can quantify how the model, how the prediction is similar to that. But the model never sees the original cloudy images. So whatever pixel in the original cloudy image that are non-cloudy, that also the model does not see. So after that, for computing this PSNR, we are considering the non-cloudy images in the original image along with the model output and how far they differ.
Try to include more quantitative measures.
Yeah, sure.
And do include the references that's missing in many of the presentations. And there are so many typo errors. You can check.
You're also talking about like prediction.
Yeah.
So now, you're telling like I have a date on like March 1st and then like I have a image for March 10th and it predict for March 20th.
Yeah.
From a remote sensing perspective, how do you think the spectral reflection is going to vary? Like, to, if you are going to predict for March 20th or something. The spectral reflection is what the satellite is measuring.
Yeah.
So when you take into account the spectral value, I mean, how is this going to vary and how does this prediction will be affected by that?
So like we are using the top of atmosphere values, and we are like here also we are predicting for a timestamp that the model has not seen, because for cloud removal also we are not using any cloudy images while training the model. So if we have a cloudy image, that means on that date the Landsat 8 has taken only that image. There was no other image. So we are predicting that one and after that using it for cloud removal. So in that way we are already doing that. Yeah.
From a given data set, you're removing the cloud and replacing it with a spectral
Yeah.
value. But like predicting for a new date which has not been imaged, don't you think the physical properties of the actual object would be affected
So
by spectral value?
there are certain like changes. If suppose there is some natural disaster, then that yeah.
Some change in the spectral value based on the condition of the crop or like you had shown some mangrove region, right?
Yeah.
So some physical changes in the mangrove region or something which is going to be prediction, how does it, how do you verify the prediction is correct?
Oh, so once we have predicted, we would need the original data to compare with that. So
But do you think it's valid? Like, cloud removal is okay, like, yeah, with that. Predicting a new image is my question.
yeah, because in cloud removal case also, we are like what the model is doing, it is generating a new image. Right. After that, in the post-processing, we are using that image and combining with the original cloudy image to get the cloud removed. But for the model, it is predicting a new image of a timestamp that it has not seen.
Just think of the picture. Just try to relate it to the physical aspects of the model.
Sure.
Okay, thank you everyone for joining.
That concludes the session. I would like to thank the chairs, Dr. Ramya and Dr. Shilpa, and all the presenters and participants for joining us. We'll be closing this session.